Alright, so this video is going to kick off Chapter 2 for us. Chapter 2, we're going to split into two different parts. Part 1 is about what we call limits, and then Part 2 will be about derivatives, but we'll worry about that when we get there. And for these first set of notes, we're going to talk about what is a limit, what is the definition of a limit. And really the best way, the easiest way I think for us to understand this is to think about it through what we already know in terms of rational functions. So we have this function here, and it wants us to state the end behavior of the function, state the domain, find the x and y values of any holes, x values of any vertical asymptotes, and the behavior of the graph near any of those vertical asymptotes. And what we talked about in the previous video was pausing the video, take a couple minutes, think it through. So I'd really encourage you to do this. Right now, take a couple minutes. We've talked about this in our review unit. Think about it for yourself. It's really going to help you long term if you stop the video and do that rather than just going on. So I'm going to pause just for a second. Stop the video. Do the problems. All right, now that you have pushed play again, after hopefully you taking a few minutes to go through these problems, give myself a little bit more room here. Okay. So the end behavior. Now, in Chapter 1, we reviewed quite a bit of end behavior, and there's those rules that you can remember from Math 4, from pre-Calc, that say, well, if it's a rational function, a polynomial over a polynomial, just look at the degree, the highest exponent in the numerator, and the degree, the highest exponent in the denominator. And if the numerator has a larger exponent than the denominator, then the end behavior says that as x goes to negative infinity, the two ends will go either to positive infinity or negative infinity. And in this case, it will be negative infinity on the left and positive infinity on the right. And there's rules about that, how you can just understand that. But for me, I think if we just take a second and think about it, it's fairly intuitive. We know that as x gets huge, because that's what we're saying. Plug in really big numbers, either really big negative or really big positive numbers. As that happens, x cubed, let's say we plug in 1,000,000. X cubed, when x is 1,000,000, means 1,000,000 times 1,000,000 times 1,000,000. X squared means 1,000,000 times 1,000,000. So literally, this first term is 1,000,000 times bigger than that term. 1,000,000 times 1,000,000 times 1,000,000 versus just 1,000,000 times 1,000,000. So this doesn't really matter. It's so much smaller than this first term. Same in the denominator. 1,000,000 squared is literally 1,000,000 times larger than just 1,000,000. So these don't matter. Even putting the 6 in here doesn't really matter. And there's mathematical ways we can justify that, but for right now we're just going to kind of think about this intuitively, just like we did in Math 4. So that means what I really have for my function, when x is big, and only when x is big, our function f of x is approximately the same as x cubed over x. Over x squared. Just looking at those first terms, ignoring the smaller terms that don't matter relative to the first term when x is big. So that can, of course, simplify to just x. And if you think about the graph of x, when you go way off to the right, the graph here simply looks like that. As you go way off to the right, as the x's approach positive infinity, the y's get big, approaching positive infinity. As the x's approach negative infinity, the y's get big, but in a negative direction, approaching negative infinity. So we can see that making sense. Now, please, 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 please remember this is only true when x is big. This is only about the end behavior. The middle of the graph looks nothing like this. There's all sorts of interesting asymptotes and holes and swoops and loops. But the end behavior, we're allowed to do this, because only when x is big can we ignore the terms that are not the biggest term. All right, state the domain. Well, the domain, there are 3 things we reviewed in chapter 1 that would make something not be part of the domain. If there's an x value that makes the denominator 0, 0 in denominator. If there is a negative under an even root, and I should say if there's a 0, if there's an x that I can plug in that makes the denominator 0, if there's an x that I can plug in that makes whatever's underneath the even root negative, or if there's an x that I can plug in that makes the input to a logarithm less than or equal to 0. That's also not allowed. In this case, there's no roots, there's no logarithms, so the only one I'm concerned about is 0 in the denominator. If I just factor that denominator, that factors as x plus 5, x plus 1. I don't care about the numerator right now because I'm just stating the domain. Well, then obviously I can't plug in a negative 5 or a negative 1. So my domain, I'm just going to say, is the set of all x such that x is not equal to negative 5 or negative 1. That's my domain. Now if I do go ahead and factor the numerator as well, first I can factor out an x, and then that factors as x minus 2, x plus 1. So those x plus 1's cancel out, and we know what that means is that we have a hole here. Now again, that's not like the definition. It's not like, oh, okay, if you cancel, that's a hole, and if you can't cancel, it's a vertical asymptote. The reason that's a hole is because both the numerator and the denominator are both 0 at that point. And I've written this, the sub part of part C a little bit differently than maybe we're used to. We're used to hopefully saying, okay, well, what's the x and the y coordinate of the whole? But now we're saying as x gets close to negative 1, because that's the x value that makes both the numerator and the denominator 0, what does the function do? And hopefully remember, the way to find that y value is just to plug in the x value of the whole to what's left, because now negative 1 will no longer make the function undefined. So if I plug that in, I'm going to get negative 1 times negative 1 minus 2 over negative 1 plus 5. If I simplify that, I think I'm going to get 3/4. Negative 1 times negative 3 is positive 3. Negative 1 plus 5 is 4. And so that's what the y value of the whole. And another way to describe that y value of that whole is that as the inputs get close to 1, as the inputs get close to negative 1, the outputs get closer and closer to 3/4. They never actually reach 3/4 because negative 1 3/4 is a whole. Similarly here, we're not saying when x is negative 1, we're saying when x gets close to negative 1. Because we know as soon as we do plug in negative 1 to this original function, the function is undefined. And so we want to know, well, what happened close to that? Well, as your inputs get closer and closer to this undefined x value, the outputs just get closer and closer to 3/4. Now continuing on that same domain path, we know that because the x plus 5 does not cancel out, then we have a vertical asymptote there. So let's write that down. X equals negative 5. And again, if we think about this. That is the rule. If it doesn't cancel out, it's a vertical asymptote. But why is that the rule? Well, that's the rule because when you plug in values of x close to -5, or the denominator gets closer and closer to 0, but the numerator doesn't. With the whole, both the numerator and the denominator are approaching 0 when you plug in x values close to -1. With the vertical asymptote, only the denominator is getting close to 0. So what happens then when we follow this same logic and say, well, what happens when x gets close to -1? What do the outputs do? What happens when x gets close to -5? Well, you can see here that I've split this up actually into two chunks because we saw this problem last week with the review, and Khan Academy actually did a nice job of talking about it. I want to talk about both sides here. When x approaches -5 from the left and when x approaches -5 from the right. Hopefully you're watching and not just listening in the background because this is so important. This little negative here says I'm talking about the left side of the vertical asymptote. I know there's a vertical asymptote there. What happens on the left side of it? What happens on the right side of it? And we want to know, well, what actually happens? And similar to what we did here, we're just going to plug in numbers essentially really close to -5. And we walked through this in class last week as well. When we went over the one from Khan Academy. What happens to those outputs? So let's do the left side one first. So in the numerator, I'm actually going to plug in -5 because I can. I know that nothing bad happens. And I know that plugging in actually -5 and something really, really, really close to -5 will give me approximately the same answer. So I'm going to plug in -5 times -5 minus 2. Then in the denominator, I know I can't actually plug in -5 because it will be 0, and I want to avoid that. But if I plug in something really close to -5, but also on the left of -5, that's like -5.1, I'm going to get a really small negative number. Small negative number. So the numerator there, that's going to simplify. -5 times -7, if I can do my math right there. That should be 35. The closer the number I plug into -5 is, the closer this numerator will be to 35. The closer the number that I plug in is to -5 in the denominator, the smaller this negative number will be. If I plug in -5.1 versus -5.01 versus -5.00001, it's just going to get smaller and smaller and smaller, but it will always be negative because it's on the left of -5. So you've got 35 divided by a really small negative number. Well, that's going to be a huge negative number. Positive divided by negative will be negative. And 35 divided by 0.1 or 0.01 or 0.0001, that's a huge number. It's 35 million. It'll just keep getting bigger and bigger. So this output here should go to -infinity. Same thing on the right-hand side. The numerator is still going to go to 35. Now, again, the closer that I plug a number into 5, the closer the number I plug into 5, the closer that numerator will be to 35. And then the denominator, the closer the number I plug into 5, the smaller that output will be. But because now I'm plugging in on the right something like -4.9, well, -4.9 plus 5 is a really small positive number. So now my denominator it's still small, but now it's a small positive number. So that means my output is going to be a huge positive number. And that's again because plug in something really close to 5, and the numerator is just going to get closer and closer and closer to 35. Doesn't matter which side of 5 I'm on. But in the denominator, plug in something here really close to 5, and the denominator is just going to get closer and closer to 0. But now it depends which side of -5 am I on. If I'm a little bit to the right of -5, then that denominator is going to be positive when I simplify it. Thus, I have 35 divided by a really small positive number, which is a huge positive number out. I didn't say it, but notice, hopefully remember from Math 4, once you cancel out that term to get the whole, all the other math you do can be done either with the original or the simplified. Everything else will work the same. Okay. So everything that we just went through is more or less review. It's what we've been talking about for our readiness assessment. Some of the notation may be slightly different, but hopefully not too bad. Now we're going to look at the title of our section, which is the definition of a limit. So here's the definition of a limit. Pause the video, read through that as closely as you possibly can. Play it again when you're ready. I'm going to hit a couple things here. One, we want the values of x that we plug in to get arbitrarily close to some number a. That's exactly the same thing as we were just doing over here. Plug in x values that are really close to -1, but not actually -1, because I know at -1 the function is undefined. Plug in values of x that are really close to -5, but not actually -5, because the function is undefined there. And so when we say arbitrarily close, there's a lot of technical definition that you could look into there about how we define this for limits. But for now, just say that really means really, really, really stinking close. And what's super important is that we're saying, but not actually that number a, whatever the number a is. A is the number that we're interested in. So I'm going to keep swiping back and forth here. So a could be -1. A could be -5. What x value do I want? What value of x do I want to get close to? That's what's happening here. And so really, we're just taking this same idea that we did here with x equals -1 and x equals -5, and we're rewriting it only slightly. I already have this arrow notation, x approaching -infinity, x approaching -1, x approaching -5. Now we're just calling that a limit. And the way we would read this, it says, then we say L is the limit of f of x as x approaches a. So the limit as x approaches a of f of x equals some number. We probably 95% of the time we write limits like this, but sometimes we'll see this x approaching a off to the side. So just be prepared. Like every year somebody freaks out. They're like, oh, why is this one over to the side? It's really just because somebody was lazy in their formatting. That's an easier button to click than that is, but it doesn't matter. Okay. So now let's look at the next question. Given this function f of x, evaluate the following. Most of these are limits. What is the limit as x approaches -infinity of f of x? What is the limit as x approaches positive infinity of f of x? What is the limit as x approaches -1 of f of x? What is the actual function value at -1? What is the limit as x approaches -5 from the left of f of x? What is the limit as x approaches -5 from the right of f of x? Now the purpose of this problem is to recognize, hey, this is the same function we've already been dealing with. Hey, these are the same points I'm already interested in. I already asked about the end behavior when x goes to -infinity or x goes to positive infinity. We already asked about this hole at -1. We already asked about this vertical asymptote at -5. And so my point in looking at this example is, hey, these are the exact same questions as we already answered, but now you have new notation. Don't let that new notation freak you out. Our end behavior on the left is still -infinity. Our end behavior on the right is still positive infinity. when x gets closer and closer and closer to -1, we said that the outputs get closer and closer and closer to 3/4. We're just writing it slightly differently here. Now, super important to point out this next one. Well, I can still talk about a function value. What is the function value here? Well, it's undefined. We already know that. We said that -1 is a whole. It makes the denominator 0, so the function is still undefined. But it has a limit, and what that means is as the inputs get as close as I want, arbitrarily close to -1, the outputs will just keep getting closer and closer, arbitrarily close to 3/4. I don't have to break up the -1 in terms of a left side and a right side like I had to for the for the -5, because the function approaches the same thing. It's a whole, so both the left side of the graph and the right side of the graph are both getting closer and closer to 3/4. But here at my vertical asymptote, I've got one side going down to -infinity, the other side going up towards +infinity. And so again, same answers here, -infinity, +infinity. Okay, I'm going to leave you another couple minutes here to think about a very, very, very similar homework, or a very similar problem here. You can just ignore this. This got copied on here when I didn't want it to. Really similar problem. I've given you a limit. I've given you a function, and I've asked about several limits and a couple function values. So take a couple minutes, pause the video, go through that. I'll put the answers here, and if you have questions on these, we'll actually start class tomorrow by going through some of these. All right. So hopefully you've paused. I'm just going to drop answers in here with no explanation for right now. 0, 0, -infinity, +infinity, -1/6, undefined, 1/10, and 1/10. Okay.